Yeah, what I'm going to talk about today or now is about drought monitoring and forecasting. We're at the interface of hydrology and natural hazards, so it covers both aspects actually of the training course. This was not only done by myself, it was also includes a lot of contributions by Pietro, who will lead the exercise later on drought, or actually tomorrow, and Wolfgang Primusberger, who was involved last year. So last year we did a similar lecture at the training course, which was more on agriculture. But the nice thing about droughts is that it covers multiple aspects. So there are a lot of variables. I mean, everyone knows what drought is, or at least everyone knows the term drought, but probably not many of you can really give a proper definition of drought. And that's what I'm going to start with, because there are a lot of factors influencing drought, so related to a shortage of water. For example, and this is an overview paper we did a couple of years ago, inventorying the data sets from Earth observations that are available and how good are they in mapping the water cycle. And we can distinguish between storages at the left and fluxes, so the movement of water in the cycle itself. And you can see at the left that there are a couple of storages in the water cycle that are closely related to drought. Of course, there's soil moisture, what we talked about before. So in a dry year, you get less soil moisture. But there's also groundwater. A drought can be more than soil moisture. I'll come back to that later. It can be propagated into groundwater storages, for example, or groundwater is being tapped as a reaction to drought conditions, so to improve agriculture in dry years. And there's also living biomass water content. So how much water is stored in the vegetation. In dry years, you have dry vegetation, so there's less water stored in the vegetation. On the other side, there's the fluxes. I'm not going into detail on all the fluxes. You can, by the way, you can see the numbers of the annual means of the fluxes and the storages. Of course, first thing if you think about drought is precipitation. So a shortage of precipitation. But it's not only precipitation driving drought, but it's also evaporations and land evaporation. So how quickly is the soil, or how strongly is the soil drying out? Then there's the groundwater. You have the groundwater storage, but you have also the fluxes. So in wet years, there's a recharge of groundwater. In dry years, in many areas, or in heavily irrigated areas, actually groundwater is decreasing. And this irrigation water use is shown at the lower right box, is called blue water use. That's the amount of water used for irrigation. So approximately, based on observations, you can say it's 4,000 cubic kilometers water per year are being used for irrigation. What you can see as well, it's not related directly to drought, but you can see also the numbers and the uncertainties. So some of the fluxes and storages don't have uncertainties at all, because we just don't know how much it is. So to come back again to the definition of drought, so what is drought? We can start with something called natural climate variability. So we have the, for example, deficits in precipitation, so it's a decreasing amount, but also, for example, it can come in very short, intense episodes, leading to a lot of runoff. So you may have in total a total of a lot of precipitation, but a big part of it runs off, so it's not contributing to soil moisture, so that can also cause drought. In the end, it may lead to reduced infiltration, runoff, and deep percolation of the groundwater. And on the other hand, there are other drivers, for example, temperature, vapor pressure deficit, causing, so dry atmosphere causing a strong evaporation. So that also there's a connection to the drought. So it's not only precipitation. So if we look at these meteorological components, we also speak of meteorological drought. And in the end, it may lead to, if it continues long enough, it may cause soil water deficiency. And in the end, it may also have reactions and may have effects on the canopy, on yields, on agriculture. And in that case, we talk about agricultural drought. So that's really the effects of a lack of water available to plant growth. Then if the drought propagates in time, gets more intense for a long period, it may eventually influence the water cycle. So for example, the reservoirs are empty, groundwater is depleted, lake level is decreasing, and so on and so forth. In that case, we talk about hydrological drought. So there's a strong, at the right you can see, or at the left you can see the time duration. So the longer the drought is, if you have one dry day, you don't yet talk about drought. But if this accumulates over time, then you get into from a meteorological drought into the agricultural drought and hydrological drought. And in the end, it may even have far-going impacts on economy, for example. So food prices, food commodities. Social impacts may even lead to migration, for example. Environmental impacts. So if there is a continued drought for a long period, ecosystems may change or tip into another state. Especially if you have longer periods of drought or multiple years of drought. You may have heard about insect outbreaks like bark beetles, which are spread more vigorously when there's an ongoing drought, when the plants already affected, the trees in this case. So as you can already sense, there is no proper definition of drought because there are multiple facets of it. So there is not a metric like soil moisture you can say, okay, there's cubic meter per cubic meter. For drought, it's much more difficult. It really depends on the scale you're looking at. So it can be expressed in various ways. For example, now if you look at a map from Australia, this is the rainfall in January, April last year. You see nice patterns. So in purple shades, you have areas where there's more precipitation in that period. You have the dry interior of the continent, but it doesn't say if the interior is in drought conditions or not, because drought is always relative. So if you have a desert, it doesn't necessarily mean that there's a drought in the desert, it's just always dry. So it always refers to a normal condition. So it's an anomaly, a deviation from normal states. So if you look at the anomalies for the same period, same continent, you see that the areas that commonly receive a lot of precipitation, like for example Northern Australia, actually did receive much less precipitation in this particular period, and there was a drought in that period. So that pattern looks very different. So we're talking about anomalies from the normal long-term mean. But there are other ways to express drought. So you can look at the millimeters of precipitation, but of course, if you have 100 millimeters less precipitation in a very wet area, that might not yet be drought. But if you have this in a very dry area where you only receive 200 millimeters per year, so you receive 50% less of precipitation, this is a much stronger drought. So you can also look at, for example, quantified by percentages of the long-term mean rainfall. So the deviations in percentages. And again, you see different spatial patterns. So it really is about how to compute the anomalies from the normal conditions. Yeah, here is, for example, the difference. So here you see an area where the anomaly from the long-term mean is much wetter. But if you here, you see a very different some different patterns. So let's go back to, so this was based on rainfall, but we would like to know more about what is available to plant growth. So what is available to agriculture, for example, or to ecosystem functioning. So we have the same map again, and now we would like to see how does that reflect in soil moisture. And actually in this case, Australia is always a very nice continent to work with because our retrievals are good there. It has semi-arid climate in most of the regions. So there's a lot of interannual variability, also caused by ENSO, El Nino, La Nina, and you can see very nice, clear patterns. And, so for example, what you can see here, the precipitation anomalies, the rainfall anomalies, and at the right you see how that reflects, how that transfers into soil moisture as observed by the C3S soil moisture product that I showed before. And then in general, the patterns are very closely matched actually, apart from the north west. So yeah, so if you want to quantify drought, you need to correct for differences in climate. So if you here, this is sorry for the German. This is this is spring 2022 in Austria, and you can see the absolute volumes or amounts of precipitation, so ranging from 30 millimeters to 228. So 13 is very little, of course. That's for our climate, so it's a similar climate as maybe slightly wetter than it is here. And you can see at the right that there is a very strong deviation. So you can talk in percentages of deviation from the mean state. Yeah, so now the question is, how do we, basically, now maybe I should mention this. I think one slide is missing. But what I wanted to mention is that, so the same amount of so if you look at the map at the left, there is the distribution seems very flat. So everywhere is roughly the same amount of precipitation. But if you refer that to the climatology, so the mean seasonal or the mean conditions, you see that in the west of Austria, so in Tyrol, the mountainous area, the same amount of precipitation leads to much stronger anomaly than in the eastern part, which is generally drier than the west. So now the question is, how can we, so where is it dry and where is it not dry? And one of the things to do so is, for example, using normal distributions or distribution deviations in terms of standard deviations. So make it different pixels on Earth, on land, comparable. So this is what you're going to use also in the exercise, which is a standardized precipitation index. And what it does, it fits the actual long-term precipitation to a probability function, what you can see here. So this is the probability of precipitation. So the accumulation for a normal period, for long periods, so climatological mean, let's say for 30 years, so the standard meteorological reference period, and the probability of getting moisture, so precipitation values below 500 is only 10%, and getting precipitation amounts above 1500 millimeters also is 0.9, so also about 10%. So it's the extreme tails. So what if you have, for example, a year where you receive 1,000 millimeters of precipitation, or a month where you receive 1,000 millimeters of precipitation, which is a lot actually for a month, but let's stick with the year. You can see how likely is it to get that information. Well, if you propagate that to the distribution and map that to the to this curve, then you get a probability. An SPI shows you actually that is the standardized precipitation index is nothing more than converting measurements, amounts of precipitation into a Z-score. So you can see if you have 1,000 millimeters, you're pretty close to the natural mean. So you're slightly in the positive, but it's not more than one standard deviation. In this case, 1 is 1 standard deviation, 2 is 2 standard deviations. So you're in the normal range of precipitation. So this is one way of expressing soil moisture anomalies as a drought index. Yeah, and then you can decide to categorize, because decision makers, for example, they like easy pictures that can be easily interpreted. So you categorize that, for example, in 7 classes. So you see, well, everything above 2 is extremely wet, everything below -2 is extremely dry, and different gradations in between. So yeah, this is one way to express drought. That can be done with precipitation, but you can also do it with soil moisture, and I'll show that later on as well. What it does, it makes a couple of assumptions. So you assume basically in this case that drought is really driven by precipitation and not by temperature or evaporation, potential evaporation. And that precipitation and other variables are stationary in time, so there's no linear trend. Because of course your climate may also change into wetter conditions or drier conditions. So you always working against a baseline period in typically 30 years. And in the exercise, you can also play around a little bit with the baseline period and what effect that has. Yeah, and then you can, for example, you also need to account for seasonal differences. So this SPI, for example, you can compute it for a year. But a yearly mean does not necessarily tell us a lot about drought. It may, but it may, in many cases, it is not. And this is, I like this example very much. This was also from last year. You see the distribution of precipitation in Austria again. And you see there's a very similar distribution in February and October. And it's exactly the same pattern, basically. So the amount of rainfall is almost the same. But if you look at the drought pattern, so the anomaly, it's very different because in different months, there's a different expected or mean amount of precipitation. So you have a very, well, not very, but you do have very different patterns here. For example, in the east is much, for the same amount of precipitation, the surface is much drier than usual than in October than in February. So if you compute an SPI, you can compute that for a year, but you can also compute it for a month, which is also, so you need to take all the monthly values for a period of all the monthly February values for a long period, and you compare your year to this reference periods. Yeah, and who actually has heard about the SPI? Quite a few. Yeah, okay. So SPI is it's broadly used because it's simple. It just needs precipitation as an input. It's not very comprehensive because of the very same reason, it only uses precipitation. And as we saw before, there's more to drought than just precipitation. There's also potential evaporation, for example. But the SPI, you can compute it for longer periods. And so you can aggregate it for 1 month, because you can also do it for 2 months, for 3 months, for 12 months, even 24 months. And you can see the longer the integration period, the lower frequency, the more lower frequency patterns you get. So in the 2-month SPI, you see a lot going up and down. But if you move towards longer periods, at the bottom you see 22 periods, then you see there is a very much longer, lower frequency signal in there. And yeah, as an example, so in the 1950s or the 1960s, there is, yeah, you see some variation here, but if you integrate it over a longer period, then you see that's really a period of very wet conditions for multiple years actually. And this type of information, for example, the 2-month SPI relates more to, for example, service, agriculture, and the 22 months relates more to what's happening in the hydrology, for example. Do we have a high base flow, low base flow in the rivers, or is groundwater recharged, and so on. Is that clear? You can always interrupt me. You can always raise your finger. We don't have to wait until the end. I mean, this is a course. It's not a conference. Okay. So, in order to overcome that, or to make it more comprehensive, the standardized precipitation minus evaporation index was developed. And that is this kind of climatic water balance. So it's the precipitation minus the potential evapotranspiration. And it basically considers what potentially evaporates again. So it takes into account the atmospheric demand, which really differs a lot between now, September, and, for example, July, as you can imagine. Yeah, and that's shown at the bottom. Yeah, the SPI again and the SPEI again. So it's not very up to date, this figure, the period. But you can see there is some differences. It's not very strong, but there are. It makes more sense to include also evaporation, especially if you consider climate change, because your precipitation may remain the same. It does not always, but it may. Let's imagine your precipitation amounts stay the same despite climate change, despite global warming. Your potential evaporation increases because there is a higher temperatures, there's a higher atmospheric demand. So your signal changes. So you get stronger drought conditions, even though you have the same amount of precipitation and even though it may be equally distributed, same as before. And that is shown here. So yes, the SPI here at the top, so an 18-month integration time. SPEI at the normal one for normal conditions, current conditions in the second row. And then there are the scenarios of increasing the temperature, so increasing the potential evaporation at the bottom. And you see that that the drought periods, so all the negative periods or drought periods, they get much more intense and long lasting. So there's less recovery if you increase the temperature by 2 degrees or 4 degrees. So if you increase the potential evaporation. So coming back to our core expertise again. So our expert is in the room, Pietro. No, can I call you like that? Yeah. So what we've been trying to do is doing the same thing. So the SPI concept for applying that to soil moisture. So soil moisture is actually what remains of your precipitation after evaporation. So also taking into account potential evaporation or actual evaporation. Yeah, like I said, we're trying to do. So soil moisture should basically reflect the combination of precipitation and evaporation. So that's actually, theoretically, that would be an even better agricultural drought indicator. So actually that is what it remains in the soil and is accessible to plants. So what we try to do is to use the same framework as for the CCI product to compute a drought index. So combining all these sensors. Currently we're in the process still of doing this. To get a long-term record of drought conditions, so Z-scores basically. It seems to work well, but it's not so straightforward as we thought, because satellite observations, if you have such a long-term data record, you have differences between time periods. We saw that before. So we are in the 1970s, we only had one observation per week at most. Whereas in the more recent years, we have multiple observations. We have maybe 5 different sensors at one location. So we have much lower noises. And also noise, if you're not careful, noise translates into very high outliers and maybe it can be interpreted as high, as strong drought. But if you look at SMASI, yeah, that's the only acronym that was still available, basically. There are so many drought indicators. I will show you later. So we came up with SMASI, soil moisture anomaly standardized index. And that shows the anomaly of the severity of the anomalies in the soil moisture product, in the long-term soil moisture. And so this is basically also the Z-scores in blue greater than 1, so 1 standard deviation. In pink, greater than 2, so very strong. And on top of that, in the purple dotted line, it's the Southern Oscillation Index. So that's an indicator of ENSO conditions, so El Nino, La Nina. So high values are indicate La Nina conditions, and for example, low values of this SOI indicate El Nino conditions. So maybe you remember still, so in 2015 there was a very strong El Nino. Also now there is an El Nino, so this index goes down. And in many cases also this goes in line with this, or the soil moisture goes hand in hand with this SOI index, because there's such a strong interannual variability as well. But you can see also here, for example, this is clearly an outlier, I guess. So that reflects, that indicates there's a very high, very strong drought, but that must be interpreted with care. Yeah, so drought, so how do we get access to drought information? There are various portals. For example, this is an example of the US drought. No, I don't have it at hand. So it's the US drought portal. But often you cannot find, what you find in drought portals is often an index. So like before, you see here again this exceptional drought, extreme drought, severe drought, normal conditions, and so on. And some combination of Earth observations, meteorological observations, even modeling. So many variations have been developed. So I showed you the SPI and the SPEI, but there are many more drought indicators which go more towards, so for example, Palmer Drought Severity Index, which is based on precipitation and temperature, self-calibrating PDSI, which is more fine-tuned for local conditions, and many, many more. So, but the nice thing about these indices is that you can use them not only to see, well, it's a strong drought or not, but also, for example, to get numbers which may eventually be more important. So not a snapshot, but integrated over time, for example. So you can get an estimate of drought duration, so the number of consecutive days or months with a certain index below 0. So you get a real length of the period. Particularly if you want to study climate change or how drought conditions are changing in time, this may also be interesting. So not only the absolute value, but also the length of the period. Or the severity. So a period can be very long, but the drought is not very strong. But you can also have a long period with very strong anomalies. So you have to, you can accumulate or sum the values, the negative values. You get an indication of the severity of the drought. Or you can combine the two and you get an indicator which is called drought intensity. I skipped to this slide, but I don't think, well, what I can mention on this is that there are myriad of drought indices around, and it's not always easy to choose one. And you also need to be careful how you interpret one. So because the ranges are different, so some of them use Z-scores, but others, for example, use percentiles, like you see in the second column, CPC, soil moisture model percentiles. Or stream flow or standardized precipitation index. So it really depends on the drought indicator. So if it's one indicator says exceptional drought, this may not be the case. This value in another indicator may be just a moderate drought. For example, SPI of -2 or less is called an exceptional drought. But here in the Palmer Drought Severity Index is only a moderate drought. So you need to be very careful if you use such data, how really look at the units and the scales. One of the portals which is closer to home, or for us at least, we're here. Maybe there are people from the US, I'm not sure. Is the European Drought Observatory, which is being hosted by the European Commission, by JRC. And they amalgamate different indicators of drought. So one of them is soil moisture anomalies, so based on models, but also on observations. Precipitation index, FA-PAR, so which is an indicator of photosynthetic activity. Low flow index, so that's an indicator of stream flow, even heat and cold wave index, and the combined drought indicator really integrates all these things. So that's used to monitor both the onset of agricultural drought and its evolution in time and space. So this is really being used as a tool to make predictions, to make estimates of food shortages, of commodity prices, and so on. So really, for the Commission, European Commission, to be proactive. Yeah, so this is just an example. So you see here, this is SPI. There's the ensemble soil moisture anomaly coming from observations. Then there's the FA-PAR, so that's the greenness of or the intensity, the photosynthetic activity, stream flow, and in the end you end up with a combined drought indicator which integrates all these different components into a more comprehensive indicator of drought. I'm not sure how this is being combined exactly, but yeah, and this is, I just wanted to show you an example, and this is from last summer. I'm not sure, Poland. Who's from Poland? There's no one from Poland, yeah. There is. I was already surprised. Can you remember July? Was it, according to the Drought Observatory, it was a dry month. Yeah, I know that memories are really short term. You know what had happened yesterday, but yeah. So I know that from Austria and then Germany, it was the first month of the summer where we really dried, and it swapped again in August. But yeah, this is what you get. So you really got, well, not in Wrocław, you didn't get a warning, but in the northern parts of Poland, there was a warning or an alert. So, but it also shows you, for example, periods where the indicator is decreasing or getting back to normal again. So in the blue areas, for example. So there's a recovery of the drought conditions to more normal conditions. So I really encourage you to have a look at the Drought portal. It's a very nice tool to play around and also to verify if that was really the case, because it's more than weather. It's not just rainfall, like I said, it's also using many other things like vegetation activity. Are there any people from Czechia? No? It's not that far away. I'm not sure, where are we? Somewhere here, I guess, no? Wrocław? Somewhere north of Czech Republic. So it was in, my Czech is not that good, but it was also in July. And so this is sucho, I think it's drought in Czech. Yes, it's right, yeah. So this Drought portal is hosted by the Czech Globe, and they really use also a modeling framework where they use also satellite observations, but mostly meteorological observations to compute deviations from normal conditions, and a very similar scale as for the PDSI. So you see here extreme drought as 5. You see how much of the land surface was under extreme drought conditions and so on. And you see that after July it decreased again, and actually in August was very normal month, or even towards the wetter. And now we're here, and it's even getting a bit into a drought again, but slightly only. And they use it also to make yield predictions. So they feed it in crop modeling and to make update yield predictions for the end of the season. That brings me to the next topic. Are there any questions on the general drought part? No? So now we're going to zoom in a bit more. So that was more about the methodology, how you can compute a drought index from observations. Now I would like to focus a bit more on what can remote sensing do to assess drought impacts or assess drought conditions, but also their impacts on vegetation. Impacts on vegetation is not a surprise. So that's somewhere in the category agricultural drought. So what is actually, soil water deficiency, so what is available to plant growth, and what effect does it have on crop health and crop conditions, and eventually on yield. And of course, anomalous yields can have an impact, economic impacts on the food prices, social impacts, migration, environmental impacts, and so on. So this is where we stand with this Earth observation part. So very shortly, so in a nutshell, a reaction of plants to water stress. So if you have water stress, the plant itself can adapt to it. So if there's not sufficient water, the plant can lower or reduce its engine, so it reduces photosynthesis. Who knows about plant physiology? I know, of course you do, but yeah. I mean, I'm not a biologist or ecologist, so I'm just explaining this from an Earth observation perspective. But what happens is, if there's water stress, there's less water available for evaporation. So what the plant does is it closes its stomata. So reduced stomata are used to exchange CO2 and water from the atmosphere and then use it for plant growth. So it's for use for takes CO2 out of the atmosphere and uses it for photosynthesis. So if there is a reduction in water, it causes a reduction of evaporation, and at the same time there's a reduction of photosynthesis. And you have different tools in remote sensing to monitor different stages of photosynthesis or drought impact. And this is very schematic. There's much in between. But the first thing that reacts is fluorescence. Who knows what plant fluorescence is? Okay. So basically what happens is a leaf tissue absorbs radiation, and a tiny part of that, if the plant is healthy, if there's enough, then there will be a tiny of that is being absorbed and re-emitted again. So plant actually glows a bit. It sends out radiation. And this process, when there's stress, can be a pest outbreak, but an obvious is water stress. If there is stress, this signal that is really emitted by the plant itself, it reduces immediately. So this is one of the first signs of plants' reaction to stress, like water shortage, is fluorescence. So you can measure fluorescence by various satellites. Now a FLEX mission is being developed by ESA. It's an Earth Explorer, which is the first mission really dedicated to measure fluorescence of the canopy. You can, for example, there is leaf water reduces, so there's less transpiration or evaporation by the plant. So the water level in the plants reduces, and you can measure that ideally by active or passive microwave remote sensing. So the vegetation water content decreases, And you should, in theory, able to measure that using active or passive microwave observations. But also, if the leaf tissue is really damaged, you can see that there is a reduction of photosynthesis. So you can measure that with optical data. Or if there's really stress, that can decant the temperature. So if there's less precipitation, less evaporation, the temperature of the plant, of the canopy, increases, and you can measure that by thermal measurement systems. So there's a whole range of measurement systems: fluorescence, thermal, passive optical, active optical, which is LiDAR, which is giving you information about the structure, SAR, passive microwave, which is not in here. But all in the successive stages of drought impacts, there are different remote sensing technologies that give you information. So, yeah, I think it's nicely explained in this figure. So fluorescence, temperature changes. I mean, it's not one-to-one matches. Leaf water, pigments, so chlorophyll. And in the end, even morphology changes. So there's a shed of leaves, it loses leaves, or the leaves drop, or the inclination of the leaf changes, and you have really geometric changes, which can be measured, for example, with SAR or LiDAR. This is one early example of, early example not, but it's an example from a paper, so already pretty old. But I think it still nicely shows you the how tightly moisture, so soil moisture, and vegetation activity are linked. And these are linked through evaporation. So yeah, at the left you have evaporation. In the middle, soil moisture, and here you see NDVI. And here again is it shows the Southern Oscillation Index, which has a positive phase. So you have La Nina conditions. And you see how closely correlated that is to SOI, so evaporation, soil moisture, and NDVI. So once you can get into El Nino conditions, you have less soil moisture and also less plant growth. And not only in Australia, but also, for example, in southern Africa. And the opposite is also very nice. In years of El Nino, you have the opposite sign in, for example, Eastern Africa. So wetter conditions in Eastern Africa than usual. Yeah, and this is in here expressed in terms of anomalies. So you see El Nino anomalies. Here you see that there's less evaporation in El Nino years in Australia, Southern Africa, northeastern Brazil, northeastern South America. You can also see that's partly in soil moisture and also in NDVI, some plant activity. So they're very closely coupled. And at the bottom you see La Nina conditions. So there's the opposite is sign. Yeah, you have a question, right? Sure.
How is related the first one, A, how is related to evaporation? I'm not sure it's written correct. It should be evapotranspiration or potential evaporation, because terrestrial ecosystem doesn't actually evaporate.
Yeah, there's a
Is it evapotranspiration or potential evaporation?
It is actual evapotranspiration.
Actual evaporation.
Yeah. So it reflects water availability mostly. Yeah, particularly in semi-arid regions. Does that answer your question? Yeah. Yeah, and then we're coming back to how can we? Of course, I have a strong slide. I would say a strong bias towards microwave remote sensing, because our department is mainly focusing on microwave remote sensing, not an optical one. You have other lectures on that. You've seen this slide before, on the upper right figure. So we're at the vegetation optical depth quantifies the attenuation of microwave radiation by vegetation. So it can be active or passive microwave radiation. And that is related to vegetation, water content, and biomass. So the amount of living biomass plus its relative water content. So you can have a lot of biomass but low water content and so on. So that's two components basically. Then there's one thing. VOD is not a geophysical variable. I mean, it's being used a lot and more. And it's really an important variable because that's really something on top of what you can measure with optical systems like shown here, active. So it gives you information, but it's not a geophysical variable. It's not a quantity like, for example, leaf area index, which is square meter per square meter, or soil moisture, which is cubic meter per cubic meter soil. VOD is a model variable, and that makes it a bit complicated to use, but also to explain it. And I think Bernard did a very good job. But you need to be aware that VOD depends, of course, on vegetation, water content, on biomass, but it also depends on the wavelength, so on the frequency of the observation. That means, for example, L-band, which has a wavelength frequency of 1.4 gigahertz, is better able to penetrate to the canopy, or at least the upper layers of the canopy, and does give you more, has a lower vegetation optical depth. So it's a radiative transfer variable. Then, for example, Ku band, which has very short wavelengths, high frequency, short wavelengths, and penetrates much more difficult through the canopy. So typically, VOD values of L band are much lower than those of Ku band. This also means that they give you different types of information. So I think it's very nicely shown here, at least for X and C band. So X band gives, so let's imagine you have an optical observation from an FA bar, a leaf area index, or NDVI. You really only scratch, or mostly scratch the surface, because the wavelengths are way too small to penetrate through the leaves. You can only get information from deeper layers in the canopy through gaps in the canopy, mostly. With X-band, you penetrate a bit deeper into the canopy, so you get more, not only the surface of the canopy, but a bit below that. C-band even more. And with L-band, I would have drawn that maybe a bit differently. With L-band, you do not only get a soil signal, but you get also information from the trunks, for example, and the branches. Because the wavelengths of the L-bands, which is 20-25 centimeters, they're long enough to travel, to pass through the leaf canopy. So it gives you more, the woody components. And this variable can be retrieved with multiple, from multiple observations, both from in the active and passive microwave domain. Now I'm going to show you, I'm not sure if we still have this in the exercise. We do, huh? Vodka. No. Okay. We did last year. So, we do have it, yeah. So, vodka, that's something we developed. So it's very similar to the CCI product, soil moisture. Vodka is also Polish, I guess, no? But we thought it was a funny acronym for a vegetational optical depth climate archive, and is a name that sticks to people. But it's hard to Google because you Google it, you only get bottles and not any microwave products. Anyway, so the VOD climate archive, what it does this very similar thing as we did for soil moisture, for ESA CCI soil moisture. So we use multiple sensors So this is the time frame covered by individual sensors. So you see here AMSR2, WinSat, M3. And we decided to combine those into one time series so that we have time series that are long enough to do climate studies, to have anomalies from long-term records. And we did this for different frequencies, so for C-band, X-band, and Ku-band. And what you can see here is what I told before. So this are the spatial patterns of VUD, and they look very common if you ever had a look at the globe, and I think you all did. So you have higher VUD values of more densely vegetated areas here in the tropics, the boreal forests, Southeast Asia, and low values, very low values, of course, in the desert regions. And what you can also see here is that C-band, X-band, and this is Ku-band here. You see that the range is different. So this goes a maximum of 0.6 for C-band, for X-band 0.7, and here goes 0.1, 0.1. And for VUD, it's even lower. So that's what I said. It's not a geophysical variable. It really depends on the observation frequency wavelength. But the patterns are very similar. For the higher frequencies, for VUD, it's a bit different because you get more information from the denser canopies and slightly less information from the sparsely vegetated areas because you get a stronger soil signal. Yeah, and this is what you, this is what you see. So bare vegetation, bare soils, shrubs, and trees. So that's what you would expect as well. So VUD increases with vegetation cover. Yeah, what is this L-band or this correlation? What is this vodka? What does it show? This is the correlation with leaf area index for L-band, which is based on SMOS and SMAP. And you see, if you look at the correlation coefficients, they're actually not that high. They do not correlate that well to leaf area index. So there's little correspondence between VUD from L-band and photosynthetic activities, so variations in leaf material. Even negative correlations in many regions, for example, here in the irrigated areas. For the anomalies, it's even worse. But if you go to a higher frequency, for example, from Ku-band, from short wavelengths, you see that the correspondence with leaf area index is much higher. So if you ever decide to use VUD for some studies to look at trends or climate change or anything, droughts, then you need to keep that in mind, that the frequency does tell you something about different parts of the canopy. So Ku-band is very good to monitor also sparse vegetation, but L-band, you see it's very limited, but gives you more information maybe about dense tropical forests. Yeah, and you can use this type of information for example, for trend analysis. So this is our trends for 25-year period. No, sorry, 35-year period. So you see a wetter increasing vegetation in India. Do you have an idea what that might be? Why it gets much wetter in India? No? Yeah, it's an expansion of agriculture and irrigation that you can see here. You see also in Eastern Europe, there's an increase in VUD, which is related to abandonment of fields after the breakdown of the Soviet Union. Yeah, and there are more signals. So there's an overcultivation, overgrazing in Mongolia. So there the density of the flocks of the sheep and goats is much too high. So you see a land degradation signal in here. And there are many other signals. Yeah, deforestation is not so well visible, but yeah, and this can be used for various things. For example, to look at the climate. So this is the State of the Climate report, again, based on European State of the Climate report. So what we've been doing is looking at anomalies in VUD in April, May, June. and April had a late frost event, so a lot of crops were damaged. And what you see here is the VUD anomaly. So in brownish colors, you have lower VUD than normal in May, which is still a result of the very late cold episode in April. So that's so you see that there is a very long-lasting signal, a delay in the growing season caused by this frost event. Or you look at state of the climate again. So the anomalies for 2022, which are very similar to those of soil moisture as we saw. Yeah, I start repeating myself, but this is very similar as SMASI. We did this, actually this was first. So we developed the standardized VUD index, which should be is a sort of drought indicator based on vegetation optical depth. So an indicator of vegetation anomalies. And based on this long-term climate data record of Vodka. So you see some variability, but not so much for this area. But if you look again so what can it do? Such an index. This is again an example for Australia, a very thankful continent, is that you see SWODI here. You see precipitation anomalies, so standardized precipitation anomalies, and you see it always matches 1-to-1 this pattern. So there's a very strong link between precipitation and vegetation activity in Australia. Same here for a dry year, 2019. Also very close correspondence. And here again, this SOI signal in purple and the blue and pink, the VUD anomalies. Yeah, and why do we need SWODI if we have, I don't know, other conditions, if we have NDVI or if we have, for example, temperature condition index. It gives you a different estimate, different insight into canopy behavior. So it gives you information of a different stage of a drought. So if you have very strong drought with very long-lasting consequences, this is strongly shown by this VUD because it really it measures how drought affects plant water content, which is which usually follows indicators, for example, from optical indices or thermal indices. I think and do 2 more slides, and then I think I can let you breathe for 5 or 10 minutes, maybe. Yeah. It's a good thing, yeah. Yeah, a lot of people do that, and we tried it ourselves as well. It can be done. It's not so straightforward because the relationship is not linear. But microwave remote sensing is actually being used for measuring biomass, for retrieving biomass. For example, the biomass mission, if you've heard of that, that's a P-band system. Yeah, so it can be. So microwave is the best suited, together with maybe with LiDAR, best suited for mapping biomass. Yeah, and that can be done directly from brightness temperatures as backscatter, or it can be done indirectly through VUD. This is, I'm not sure if I have to show it, but no, I just briefly show it. So this is the correlation and temporal shift in weeks between SODI and ERA 5 soil moisture. As you can see, basically how it correlates different layers. So 7 centimeters, so this is the surface soil moisture layer of ERA 5. This is the 7 to 28 centimeters and 28 to 100 centimeters. And you see the correlation strength. And you can see the shift in weeks. So you can see that the correlation is strongest after a couple of weeks. So which indicates that VUD shows you actually the it shows a strong link between deeper soil layers with some delay in time. Yeah, just to summarize VOD. So it profits from the long heritage of high-frequency microwave missions, so we can go back long in time. Of course, SMOS and SMAP, they provide very valuable observations of biomass, even if they were designed for mapping soil moisture. They have a strong biomass signal, particularly in the more densely vegetated areas. But if you use also the higher frequency observations, you can go back much further in time. So it's a nice addition. Yeah, and this vodka, so the higher frequencies, so the Ku, X, and C band are particularly used for drylands, aquaculture, which have not that dense canopies, pastures. And it allows to assess the impact of droughts on global vegetation dynamics. Yeah, so the next thing is, so we have seen drought monitoring, the drought indices. What is drought? We've seen potential sources of information coming from Earth observations to monitor drought or to monitor vegetation activity. And now I would like to show how we can use this for drought impact monitoring. I think a very nice example is provided by one of our colleagues, or two of our colleagues, Mariette and Isabella, showing there was a very strong drought in 2014 in Senegal, which is a pretty strongly water-limited region. And we've been looking at different indicators, different observations. So CHIRPS is a precipitation data set. HF is a surface soil moisture. This is also surface soil moisture from microwave remote sensing. Then we have a root zone soil moisture product from microwave remote sensing, NDVI. So this is moisture the upper four, and this is different NDVI and different frequency VOD products. And we're looking at the percentiles over time, so how they develop over time for different regions. And you see this is the period June to October in 2014. And you nicely see that the drought started to develop very early in the precipitation products and the passive microwave products, but still the vegetation does not yet react to these drought conditions. You have basically the peak of the drought, the meteorological drought here in July. And only there in July, it starts really affecting the vegetation signal. So the vegetation signal drops. And then it lasts for a couple of weeks or months, actually. And in September, the meteorological conditions start to recover. So it gets, it starts to rain again. But what you can see is that in the vegetation products, the anomalies started much later, but they last also much longer. So you see the drought conditions continue to exist in the vegetation signal. And that is so important, and also, nice to see that the different products that we have from microwave observations, Earth observations, give you different insights in the reaction of plant growth to drought. So that looking at one data set often is not enough to get a full picture. So you can look at precipitation, but you don't know how vegetation reacts. And you can look at vegetation anomalies, but you don't know whether it's recovering or not. So it's very useful to look at multiple drought or multiple observables to have a proper understanding of the drought and its development. What we see here is the same region again. So what we can see is also, so this is natural vegetation, so broadleaf forest. This is shrubland, cropland here, and also cropland rain-fed, and some irrigation here along the river. And you can see at the right that different land cover types react differently to drought. And that's also important to notice. Because if you look at the onset date of the drought, but also the duration of the drought, you see that the natural vegetation is actually for a much shorter period under drought conditions. So the tree grows about for a shorter period affected by the drought. Whereas precipitation, it affects all land cover types equally. Precipitation, yeah, it rains everywhere the same amount, but the reaction of soil moisture and vegetation to this lack of precipitation is different. So both in duration and severity. So that's also important. So there's a land cover signal in the drought. I would like to conclude with an example from the close to home. This is the Pannonian Basin. This is probably you all know. So it's centered around Hungary, but covering multiple countries. And there's one study also we did in the framework of an ESA project. It's where we looked at drought and see if we can get a hold on the drought signal in yield and yield anomalies. So just to give an indication, what's the climate look like? So the Pannonian Basin has precipitation amounts of less than 600 millimeters per year. So it's not very wet. And it's an agriculturally dominated area. So more than 70% of the area is actually agriculture, as you can see at the lower right. Yeah, so it's a slightly continental climate, but with slightly higher amounts of precipitation in summer over winter. And drought, as you know, it's not only something that's happening in Southern Europe or something that's happening in the Horn of Africa, but it's also happening here. And this is just an indication. This is where we try to get information from newspapers and so on, where there was mentioning of drought and drought impacts in the Pannonian Basin. And in yellow, agricultural drought impacts, so losses in yields or dry conditions on the fields. Forests being affected in green. Soils being affected, so drier soils being mentioned. Soil cracking. Wildfires in red, so also wildfires are not something that is reserved for Southern Europe, but it's really also moving upwards to Northern Europe, and mentioning of hydrological impacts of drought. So there's quite a few years where there was a strong drought. So and typically these drought episodes led to crop yield losses, which is no surprise. And in this region, about 20 to 30% of the yields are actually lost because of drought. So less than, and that's significant. That's 1/3 of the normal yield is not there to be sold. So that has an enormous impact on the economy. And this is said to be exacerbated by climate change. So we wanted to know if we can use Earth observation to make predictions of the yield. So what is going to happen if we have a drought now? How does that affect yield in 2 or 3 months from now, so in summer? And the first thing we did is we're looking at different indicators of drought. So this is the SPEI again. This is the evaporative stress index, which is based on thermal imagery, so showing land surface, temperature conditions, and this is soil moisture as measured by active microwave sensing. And these are the impacts. So how does it impact the vegetation? So we see NDVI on top, BOD anomalies, and SIF, the one I mentioned before, fluorescence. And you see in all data sets there is a very similar pattern. SIF is a bit more noisy. That's a very tiny signal which is difficult to measure. But you see, there is potential of Earth observation to detect and even maybe predict yield anomalies. So what we did is develop a forecasting system using machine learning. We wanted to make sure wanted to exploit what can we do in machine learning. So we used the XG boosting for this. So gradient boosting methods, and we predicted the yield forecast of wheat, which is harvested in July in this area, and maize, which is harvested in September. And we did this at the NUTS 3 level, so province level. And assess the scale normal years and years of drought. So the nice thing about machine learning is you can test a lot of combinations, you can test a lot of indicators, but of course we wanted to know how well can we do with using our own products, of course, the VOD, surface soil moisture, root zone soil moisture, but also optical indices from NDVI, leaf area index, or meteorology, of course. Of course, meteorology is still the main driver, temperature, precipitation, in different flavors. So number of wet days, diurnal temperature range, and so on. And some drought indices. So is using Earth observation directly, is that sufficient, or do we also need SPEI or evaporative stress index? So more higher level information products. So we did our forecast up to 4 months before harvest, so starting in March already. And every time a new month, so it progressed in time. We did it on a monthly basis, the prediction, which is still very coarse, of course. But we added a month of extra data and did a new mapping of the forecast, of the yield forecast. This is what we get. So this is the R squared, the R squared value for the NUTS 3 level. So a different lead time. So this is 3 months before harvest, 2 months before harvest, 1 month, and at the time of harvest for both wheat and maize. You can already see the differences between wheat and maize. So maize was easier to predict. And wheat was a bit more complicated. And you also see that development at 3 months before harvest is still very difficult to predict. Harvest yield losses because of anomalies in the observables. Because still a lot may change in the period. I mean, it may rain a lot for a month, and then even though you have dry conditions in the beginning, it still changes during the growing season. So what we could show is that the high-risk correlations are about 0.94 1 month before harvest. Of course, there's not much, doesn't give us much time to fine-tune the harvest or the yield still, but at least gives you an estimate of how much will be there, and you can, all the logistics can be fine-tuned, of course, if you predicted 1 more year before, 1 month earlier. And in drought years, approximately 2 months before harvest, we could clearly start to see a drought signal, which is shown here by the bluish dots. So these are the drought years in orange. And you see that, after 2-3 months ahead, that started seeing this signal already. So you have a predictive scale of your surface soil moisture and so on yield. So which is very informative, of course. I think I skipped this slide for the sake of time, maybe. It was slightly more difficult to predict yield losses in drought years than in non-drought years, than in normal years, because drought years are extreme events. So you have, both from a meteorological perspective, you have little data to train it on, but also there are multiple factors in a drought, that complex systems, complex adaptations of plants and so on that occur during drought years, which are making more difficult to predict yield losses. Yeah, and then one of the most interesting things for us was, of course, also not how good can we predict yield, but also what is contributing to the forecast. And yeah, we could see that for wheat, temperature was the main control. So the more the grayish colors are related to temperature, but particularly early of the season, temperature-related predictors were a good indicator of yields in the end of the season. But for wheat, towards the end of the season, so the drought indicators, drought and stress indicators, they were very useful in predicting actually drought or yield losses caused by drought. For maize, temperature was the most important at long lead time, so the grayish colors again. But what was very interesting for us is to see that soil moisture are among the main controls towards harvest. So it really, in the last months before harvest, maize was very much dominated. Maize yield were dominated by how much it still rained in these months, 2 months before harvest. Yeah, and in green you see the impact of NDVI, leaf area index, VOD. So there is some predictive skill in these features, but it's not too big. So it's mostly in the drought indicators and the soil moisture, which is of course also an indicator of drought. So to conclude, Earth observation information provides very important information for drought monitoring. But still we need to work on how to predict crop yield losses in years of severe drought, because we're still not able to properly assess the impacts, predict the impacts. And of course we need to go down with the resolution, because this was at the NUTS 3 level, but we would like to know what's happening at the field scale, for example. And we didn't include any of the Sentinel-1 products or Sentinel-2 optical data or Sentinel-3 or thermal data. So there's a lot more potential still in improving such forecasts with the novel Earth observation satellites, also the upcoming ones like LSTM, FLEX mission, maybe SIMR, which is a passive microwave signal. And one of the things we're working on currently, and Emma as well, he's in the room, is there's a very strong reaction of plants at the sub-daily time scale. So there is a strong drought signal. The plants react within the course of a day. They react to stress conditions, and we cannot monitor with current satellite fleets because they give us a daily observation at most, but more often every 2 or 3 days. So we would really like to look at this is sub-daily level. This is just backscatter, for example. So it's measured by Sentinel-1. This is from a field experiment, but you can see there's a very strong variation within the course of a day. And this variation strongly depends on the availability of moisture in the soil. So this is very, we hope that ESA will listen to us and that we can convince them that this is an important satellite and should be launched. With that, I would like to conclude. You can find more information on our teams and the work we do on the following links, and all the data sets that we produce actually are all open source, so you can have a look at them, play with them, and we're always happy to receive feedback on them, because we know the things we produce are not perfect. We can always improve things. That's why we're still working on it after 15 years, still working on CCI, because we know we can improve things. And user feedback is always very, very helpful in working on turning the right screws to improve that. So yeah, thanks for listening, and looking forward to seeing you at the exercise. Thanks.